Assalamu alaikum. We are going to explain a new chapter, chapter 18 in your books, which is magnetic field created by an electric current in 3 parts. We have different objectives in this lesson, but we want to talk in this part only about 1. Recall chapter 17, which is magnetic field. 2. Ørsted experiment. 3. Magnetic field created by a rectilinear wire carrying current. You know that any magnet has 2 poles, north and south, that can't be isolated. So like poles repel and unlike poles attract each other. It's important to know that a magnetized needle, which is free to rotate about a vertical axis, indicates the magnetic north pole of Earth. The north pole of this magnetic needle points toward the south pole of a magnet placed beside it. In the region where magnetic effects appear, we say that there is a magnetic field, and is characterized at each point by a magnetic field vector B. The magnetic field around a magnet can be detected by using a magnetic compass needle. This is the magnet. This is the magnetic compass needle. The magnetic vector B takes the same direction of the magnetic needle, as you see in this figure. The value of a magnetic field is expressed in Tesla, which has a symbol capital T, and it's measured using an instrument called Tesla meter. It's important to know that the magnetic field lines are closed loops. They traverse a magnet from its south pole to its north pole. As you notice in this figure, the magnetic vector B is tangent to the loops of the magnetic field. The closer the field lines, the stronger the magnetic field, then the greater the magnetic field vector B. Now, we will start with the second objective, which is Ørsted experiment. We have a magnetic needle that's free to move about a vertical axis. At equilibrium, it is subjected to the horizontal component of the Earth's magnetic field. We put a straight conductive wire AB in the vicinity of the needle and parallel to SN. So, what happens when a current traverses the wire? Now, connect the battery to the cable. When the circuit is closed, the needle is diverted, as you see in this video. Then the electricity flowing through the wire generates a magnetic field. Note that if we change the polarity, the needle also changes its way of deviation. Ørsted experiment observation. We observe that the needle deviates in a given direction, as you see in the first picture. When we change the direction of the current in the wire AB, we observe that the direction of deviation of the needle changed. Conclusion: this experiment has led Ørsted to admit that 1. The passage of a current in a wire creates a magnetic field B vector in the space around it. 2. The deflection of the needle depends on the direction of the current and its value. Look to this figure. Now, magnetic field created by a rectilinear wire carrying current. We use the following materials: a plain cardboard, a DC voltage generator, a long copper wire, iron fillings, and a rheostat. Procedure: first, sprinkle some iron fillings on the cardboard. Second, a straight copper wire stretched vertically passes through the plane of the cartoon. Finally, connect the wire to the poles of the cell by means of a rheostat and a switch. As you see, the iron fillings are redistributed and form concentric circles. Observation: after we close the switch, the current traverses the wire. We observe that the iron fillings form concentric circles that have a center is the point where the wire intersects the cardboard. Look to the following figure. Now we want to interpret this experiment. Each piece of the iron fillings is magnetized and behave like a small magnetic needle which takes the direction of field B vector at a considered point. These circles formed by iron fillings represent the field lines created by a magnetic field of the wire. These lines form the spectrum of this field. Thank you for your attention. This is the end of the first part. Recall plus verification that the current traverses a wire will create a magnetic field around it.